Hello students, welcome back to another lecture on classical electrodynamics, and today we have lecture number 26. And today's aim of the class is that we are going to see an introduction to the solution to the electromagnetic wave equation. In the previous lectures we have seen what is meant by a Poynting theorem, of course some introductory part, and then we have also seen how to calculate the energy density in the electromagnetic field. And then especially in the last class we have seen the covariant formulation of electrodynamics, which means that identifying what are the Lorentz scalars and then writing down the electromagnetic equations in terms of four potentials. So it is known as the four vector notation, and that's what we have seen in the last class, which is actually lecture number 25. So today's plan is something which will be very simple and also very important. And the idea is that if you're reading some books on electromagnetic waves, different books will write the solution to the electromagnetic wave equation like e to the power of I into omega t minus kx. And in some other books, they will write kx minus omega t. So there will be a flipping of that. Two terms will be there. That is one confusion. And second confusion is that just by flipping the two terms, can we say that it is a wave propagating in the other direction? That means if the first one is representing the wave propagating in the positive x direction, can you say the second wave that I said by after flipping, will it represent the wave traveling in the negative x direction? Is it like that? So that confusion comes. And in addition to that, you have two waves they used to write. One saying that a into e to the power of I into kx, other one is b into e to the power of minus I kx. So some kind of little confusion will be there, exactly what is what, and so that is the point that we are going to make it clear. And in fact, if you have studied, of course, if you have studied the first course on the mathematical methods in physics, there is a topic called the D'Alembert solution to the wave equation. If you have studied, then certain things will be much better. And I'll actually go to the board and show that. So here is that you can read and follow the blue color cursor. The typical wave equation, is you already know what is wave equation. It's an hyperbolic equation in the partial differential equation, and the appearance of the linear wave equation is like this: UTT. UTT means what? The suffix represent the partial derivative notation, which means actually it is the dou square u divided by dou t square. It is the second order partial derivative with respect to time. That is the UTT. Then that is equal to some constant into, mathematically speaking, it's a constant into, you have the second partial derivative with respect to the space x direction. So this is actually dou square u by dou x square. So I am writing this notation because this is the usual notation that is used in the mathematics text, and therefore in the mathematical physics course also, when you are studying the solution by the D'Alembert technique, the technique is known as D'Alembert solution method. And if you have studied, it's good, you will be having a better idea. But the point, today's point is that I'm not going to explain what is the methodology of the D'Alembert solution. Okay, that I will explain in another lecture in mathematical physics. Okay, so this lecture being a course on electrodynamics, so I would like to focus attention to the appearance of the solution to the equation. So here the point to be noted is that this being the second order partial differential equation, you have the second order derivative not only with respect to time but also with respect to the space. So therefore, coming to the initial and boundary conditions, how many conditions are required? If you see, you have to provide, or we need 4 conditions. Only then we can say the specific solution. If nothing is available, you can only talk about the general solution. So the question is, first of all, how many conditions are required? How many should be initial condition and how many should be boundary condition? That should be clear to you. Because this is a second order time derivative, you need 2 conditions. For time derivatives, you need initial condition. For space derivative means with respect to x, y and z. So because you have the second order partial derivative with respect to the space, because this is a second order derivative, we need 2 conditions, and because this is a space, you need boundary conditions. So that means 4 conditions are required, out of which 2 must be initial conditions and 2 must be boundary conditions. Only if all the conditions are given, then we can actually calculate the exact solution or a particular solution to this differential equation. So okay, so the technique what is known as the D'Alembert solution, that we will not enter into the detail right now, but instead, okay, even without knowing, suppose that you have not studied this properly, the D'Alembert method, even then, okay, without that we will be able to understand how the solution is going to look like, and how to understand which wave is propagating to the positive x direction and which one is going to propagate in the negative direction. That's what we are going to see. So for that I would like to show a simple graph that will be useful to make the points clear. So I'll show the graph now. Yeah, so here what I'm planning to show is you have the x-axis, y-axis is there. I'm going to plot a very simple straight line so that it is easy to understand. I'm going to plot y equal to x. Y equal to x. So you know how the equation is going to be. It is a straight line passing through the origin and making 45-degree angle. So I'll show it in flashing so that the line will be flashing, so that the line will come there. So as you can see, I am plotting in the red color. So that is the equation of the straight line, which is actually y equal to x. So remember the equation, y equal to x. So that is the equation for the red color line. So that's fine. Now I am planning to move this. That means I am going to translate. Translate means shifting, moving. Take this particular straight line and then move it to the right side and keep it wherever you like. We can keep it anywhere. We can keep it at 2, 3, 4, or wherever we can like. So let us therefore do that. I am planning to translate this and keep it, but I'll take a copy and then show. In the green color I am showing. Okay, I don't want to disturb the original one, so let the original one be there. So let us assume that I am taking a copy of that and then I am translating like this. So how I am moving is very important. I am not going to move the straight line in the vertical direction. I am not going to move that. That's important. I am not going to move this red color line in this direction, some kind of arbitrary direction I am not going to move. So that's important. In which direction I am going to translate, in which direction I am going to move or shift is that properly along the x direction I am going to shift. So therefore, essentially I have shifted like this and then I have kept it here. That is how this particular straight line has come. Now the question is a simple question. The question is, what is the equation of the green line? That's the question. You already know what is the equation of the red line. The red line is y equal to x. So what is the equation of the green color line? So this is the first question. Second question is, similarly, suppose if I am going to move it to the left side, I'll be getting this kind of purple color line, which means that I am taking a copy of the red color line and then translating or moving to the negative direction of the x-axis and then keep it at -4. Of course, -4 is not visible. I'm going to keep it similar to +4. There's a -4 there. There I am going to keep. So that is the method by which it is generated. I am repeating. I am now giving explanation because apparently it will look as if I have shifted in the y direction and kept it at 4. That is how it may look if I don't explain. That's why I am taking some time in explaining. Okay, it will appear as if I have translated the red color line and kept in the y direction 4. I did not do that. That's what I am telling. How I generated the violet color line is that I have translated the red color line in the left direction and then keep it at x equal to -4. So if you do that, the question is, what is the equation of the straight line which is in the violet color? That's all. So this is of course this is a very simple question, and if you know the answer, we will be getting a good idea about the direction of propagation of the wave. So let me therefore move further and show what is the equation of the curve. So here is the curve, and now the -4 is visible here. So here it is there. So I've translated and kept it here. So this happens to be 4. That's all about it. Okay. For every curve, the same 4 will not come here. Okay, that's fine. So now I am writing the equation. The equation of the curve or the straight line in the red color is y equal to x. The y is called f of x. Now the green color curve has the equation which is given by x minus 4. So therefore, if x has become x minus 4, you understand that f of x is actually f of x minus 4. So the right side is particular, left side is general. This point you have to catch. Right side is particular. What is particular means straight line. Straight line is very particular. I don't have straight line. Suppose I have a different kind of curve, then you do not know what to write here. So instead of that, writing f of x minus 4 would be much better for the calculation. So you should know that x minus 4 is the equation for the green color line. Only then this will be clear. Okay. So of course that is quite simple. That's why I'm not explaining. And similarly for the violet color line, the equation of the straight line is y equal to x plus 4. So y equal to x plus 4 is what we say. The new function is equal to x plus 4, and the new function we are going to understand that it is given by f of x plus 4. So how we are understanding is, new function is nothing but the old function which got translated in the negative direction. So now you have to be careful in catching the direction. If I am moving the red color line to the positive x direction, there will be a minus here. If I am moving the curve in the negative direction, I will get a plus here. Okay, so if I am moving in the positive direction, means the wave is going to propagate in the positive x direction. So this is how when the wave is going to propagate in the positive x direction, a minus will come. When the wave is going to propagate in the negative direction, a plus will come. So now this is the fundamental thing that you are going to understand from this, the simplest example of a straight line. And now that why do you want to deal with a straight line only, and therefore let us move ahead with a different curve. Let us consider some other curve. So instead of the straight line, I am now considering a different curve, and I would like to show some points ABC here only for references. That's all. I mean, where are the points located, whether I am moving horizontally or whether I am moving vertically, that kind of reference will be clear to you with these points ABC. Now as usual, I am planning to move this blue color line. Okay, move or a copy of that. I will not move the original one. I'll take a copy of that and then move it along the positive x direction. So let me move and show it to you. So I'm now moving and then keeping it at x equal to 2. And similarly, you can move it to any other place as you like. Okay, but remember that this is how the translation has taken place. And now, as you can see that it has simply moved from here to here. Okay, so the important point is that what is the relation between red color curve and blue color curve? That is a question. The answer is blue color curve is obtained by doing a shifting of the or translation of the along the x direction by some amount. Here it is 2. So if it is the case, you can place it anywhere. Okay, 2 or 4, whatever it is. If it is the case, the question is what is the equation? I'll show the equation now. Okay, so the original curve, what is the original curve that you have? Red color curve is the original curve. So I am writing earlier I did not tell what is the equation of the curve. So now I will write down what is the equation of the curve. It is actually y equal to x plus sin x. So that is how this particular red curve is exactly nothing but x plus sin x. Now the question is, what is the equation of the blue curve? The answer is that now it will be difficult to find out what will be the equation of the blue curve. That is why instead of struggling to the right hand side, you now understand from the left hand side. In the left hand side, what you do is, instead of f of x, you write f of x minus 4. That's what you did it for the straight line. So understanding in terms of function is easier rather than understanding in terms of straight line. And therefore, once you say that it is f of x minus 4, it means that you have to replace every x by x minus 4. So there is one x here, x minus 4. There is another x here, again x minus 4. So wherever there is an x, all these places you have to replace by x minus 4. That is the meaning of f of x minus 4. And therefore, this is the equation. And in fact, if you take a software and then plot this particular curve, namely x minus 4 into sine of x minus 4, you will be getting the blue color curve. That means you don't have to regenerate this curve using this equation, but instead you take a copy of this and then shift it. So now let us make the point clear that we will say that a wave looking like red color, let us assume that red color curve is representing a wave, then that wave is propagating in the positive x direction. If it is propagating in the positive x direction, minus will come here. That's a point to be noted. Plus will not come. Okay, so now these two things are clear. Now a wave will not be looking like straight line. A straight line will not be a wave. Okay, this could be considered as a wave because some kind of oscillatory structure is there, but practically this is or not also useful. Practical wave is usually we consider sinusoidal waves. Therefore, instead of considering straight lines, instead of considering some kind of arbitrary shape, I want to show some practically useful one, namely sinusoidal. Sinusoidal means it can be either a sine wave or a cos wave. That's the meaning of sinusoidal. Of course, tan wave is not there, only sine and cos. Okay, now I am actually I have drawn the graph for the sin x, and now as usual what I am going to do is I am going to take a copy of this particular wave and then translate it along the x direction by some amount, any amount. Okay, I may move it at 2 for example, or I'll move it at say 3.14. Here you see this is 3, after 3 this is 3.14. 3.14 is actually pi. Okay, so this is actually pi, then this will be a 2 pi. Okay, so that is how the point is. So instead of saying pi, it is actually 3.14. Okay, let me therefore translate slowly, and then you can see as it moves. Slowly I will move so that it will be easier for you for visualization. It is moving. Let me stop there at 2. Again I will move it further and then keep it at pi. And that's it. So now you see, now the question is that how did you generate the blue color curve? That's the question. The answer is we have taken the red color curve and then shifted or simply moved by an amount pi, that is 3.14, along the x direction. That is how we got it. So this explanation is required. If nothing is explained and only if you this particular curve is shown, we do not know what some two things are there which are oscillating up and down. So what is the connection between red and blue curve? This kind of clarity will not be there. So that is why this explanation. And once this is clear, we will again ask the question, what is the equation of the blue curve and what is the equation of the red curve? So let me therefore write, and that will be clear for you. Now here it is clear that I started with the red curve. Therefore the red color curve is actually the sin x graph, and the blue color curve, you don't have to struggle to find out the equation. You are only going to write down that this is f of x minus 2. The reason is here 2 is there because by an amount of 2 we have moved. That is the number that you'll have to write down. And if it is the case, all instances of x you'll have to replace by x minus 2. Here there is only one x, therefore replace that by x minus 2. And that's it. So this is the equation of the blue curve. Now we can say that the blue curve represents a wave propagating in the positive x direction. Positive x direction means minus will come. So that's all about it. So this is the information which should be clear in your mind, so that all the kind of confusions with the plus minuses will be eliminated. Okay, there is some trouble with units and dimensions. That's what I am going to explain. Okay, let me explain what is the trouble with units and dimensions. So there is a little trouble with the units and dimension when you are writing some sin theta cos theta. Mathematically speaking, you don't worry. You simply plot y equal to sin x. Okay, actually when you plot mathematically when y equal to sin x, you don't ask what is the units and dimension for x as well as the units and dimension for y, and where it is assumed that you don't have any units for mathematically treated values. That is the usual tradition when you consider any equation, whether it is algebraic or differential equation or trigonometric equation. We don't bring units and dimension into picture into the discussion. So therefore we assumed that all the variables that you are going to consider in the plotting of y equal to sin theta doesn't have any units. Of course theta will be measured in radians, but radians and degrees are not considered under the units, so you don't attach them and then do the calculation. Okay, so now what is the kind of trouble that you're going to get is that practically, since you are going to talk about some wave propagation, we need to understand whether the units like x minus 2 for example, whether any dimensions and unit is there for x. That is a question, and you must be knowing that yes, it is there, because when the wave is going to propagate along the x-axis, when it is propagating means what? The wave has moved from one place to the other, right? So that means it has moved over a distance. So therefore, I have written meter here. So certainly there is a dimension for x. That's what you understand. Now then there's a minus 2 is there. So the question is that x is having dimensions of meter. So whether 2 will have the dimension or not. So the answer is that it must have dimension. Otherwise, there is no meaning. You can't subtract two numbers with different units. You can't subtract two numbers, one with unit, one without unit. Then there is no meaning actually. Then it will be totally, it is a nonsense actually. And therefore, if x is having the dimension, same dimension should be there for 2 also. So typically then 2 should have the same dimension as 2 meters. So that is a point to be noted. But however, as you can see, 2 is actually, it should have the same dimension as meter, that is by compulsion. Then what happens is, practically what is happening is that practically wave is propagating. When wave is propagating, what happens? It is going to propagate at a particular speed. So therefore, practically there is going to be a speed of the wave. So I am writing meter per second. So there is a speed of the wave. Then the wave is going to propagate for long time, but I will be measuring after 1 second interval, or I'll wait for 10 seconds or whatever it is. So that is the time. So I'll wait for 3 seconds and then I'll measure how much distance it has moved. So that is how I calculate the time, right? So therefore, the time for which I am going to wait and measure is the time. So it has seconds here. So you see I'm writing that this is second and this is meter per second. So if you take the product of these two, that is the speed and the time, which I am writing v into t, then I'll get the meter, isn't it? So how do you generate the meter is that meter per second into second. Therefore, the meter can be understood as equivalent to v into t, equivalent to v into c. Therefore, it will be better that I will delete the number 2. Number 2 is just a specific example. In this particular case, it can be anything. Therefore, instead of saying that this is x minus 2, I will now better write x minus vt. So now we understand why it should be so, because physically it has an agreeable dimensions, and therefore I am trying to write down like that. And that is exactly what I am doing here. So instead of saying x minus 2, that's what here it is written down, that f of x minus 2 is a specific example that we have taken here. But instead of that, okay, probably I'll remove this. Some of the board is not visible. Now it will be okay. So instead of writing the f of x minus 2, it is better to write f of x minus t for a general situation. So what is our conclusion by doing this analysis is that if you write a function of, remember this is a function of, it can be any function. It can be a straight line function, arbitrary function, sine or cos function, whatever function it is. So any function f of x minus vt that represents not necessarily wave, but I am using the word wave because we have already written velocity multiplied by time. Okay, it is actually representing a translated. Mathematically speaking, it is shifted. The graph is shifted. But in physics, what happens is a graph is shifted by that amount is what in physics we say that the wave is moved from one place to another. That's what we mean to say. Therefore, x minus vt represents wave. Which wave is shifted is f of x, not x minus vt. See, f of x is the original one. Then f of x minus vt is the wave after time t. So this is after time t. So this is at time t equal to 0. So that is the meaning. So which wave is actually propagating means f of x is propagating, and after some time the appearance of the wave becomes f of x minus vt. And direction is important, and in which direction it is traveling is in the positive x direction. So minus should be there here. You keep that at a uniform speed v. The velocity v should be uniform. If it is not uniform, then this is not the situation. So at least we demand a kind of wave that is moving at uniform speed. Uniform speed means constant speed. So that is the understanding that you have, and so we are now happy that we got some kind of expression like function of x minus vt. The point to be noted is that what is that function? So that's what, let me explain that. Function can be anything mathematically. Okay, let us now see what is that function. We'll see. Now as usual, I'll write down the wave equation. This is how I started in the beginning, saying that utt equal, this is your utt. Instead of saying u, now I am using f actually. second order partial derivative is there here. The second order space derivative is there. So the wave equation is written here. Instead of using suffix notation, here it is much more clear using the derivative. Now the point to be noted is, why did we consider this equation? First point, because we are discussing electrodynamics, right? So in the electrodynamics, we have the electromagnetic wave equation, one for the electric field and one for the magnetic field. You have an identical equation to be written for the magnetic field also. Identically same. Del square into del square of the magnetic field equal to 1 over c square into dou square magnetic field by dou t square. So these two equations are known as the Maxwell's wave equations, which represents the electromagnetic wave propagation in free space. So that part is something which is quite familiar to you. Is usually the derivation of the electromagnetic wave equation is done in BSc. In fact, if it is not clear to you, or if you want to see that, you can refer to lecture number 29 in the BSc Electricity and Magnetism. Okay, so lecture number 29 you'll have to verify in the BSc lecture series, okay, not in MSc series. So there I have already explained how to derive this. Only if you want, you can see, generally you'll be knowing how to get this. You can easily get this wave equation from the 4 Maxwell's equations by taking the curl of the curl equations. That's all. It's quite simple. Okay, now what is the today's objective is that, this being the wave equation, that we are now considering the one-dimensional wave equation that is looking like this. We will come back to this at the end. Okay, and here this is three-dimensional because electric field vector is there. Here f is a scalar, so this is supposed to be one-dimensional and this is three-dimensional. So there is a little difficulty is there how to move from here to here. That part I'll do after finishing this. Okay, now that this particular wave equation is a second order differential equation, of course this is a linear. That's important. I have inserted the word linear. The reason is that we are going to make use of the linear combination of the solution. If the original equation is not linear, then you cannot make use of, or we say that linear combination is invalid. Okay, so this particular differential equation is a linear equation because you don't have unknown powers, right? All the unknown powers are exactly equal to 1. So unknown is f, right? F is unknown, so the power is 1 only. So that is the reason why it is linear. And of course other things are clear to you. And now we are going to say that it has two linearly independent solution. One function, one linearly independent solution is what is clear to you right now from our graph, namely f of x minus vt. So f means any function that you are going to consider here. That's why I have written here the f here. It is the same thing. And this is the first linearly, or we say that this is the one linearly independent solution. You must have a second linearly independent solution to this equation because it's a second order differential equation. Third order equation means three linearly independent solutions should be there. So that is clear to you. An nth degree or an nth order differential equation must have n linearly independent solutions. So therefore you are asking the question, what is the second linearly independent solution? And the answer turns out that it is the same wave, but only thing is that it has to propagate in the other direction. Other direction means negative x direction. So you see here, if there is a minus there, then it represents positive x direction propagation. If there is a plus here, it means that the wave is propagating in the negative x direction. That's all. So these are the two linearly independent solutions. And once you have the two linearly independent solution, we can make use of the linear combination because the differential equation is a linear differential equation. And if you are going to do that, of course the appearance is clear. It is there here that you can write down a combination of, so f of x minus vt is first solution, f of x plus vt is the second solution. A and b are two arbitrary constants and then you combine them, and this kind of combination is what is known as linear combination. Okay, so now the point to be noted is that I said what is that f there. F can be any function. Okay, to start with, mathematically we started with a straight line, then we started with some kind of graph, and then at the end we have seen some kind of sinusoidal graph. So which means that mathematically speaking, any kind of arbitrary shape can be chosen for f. That is our mathematics space. But physically we don't want to do that. You see here, physically what happens is when you are studying waves and oscillation, Usually when you study the waves and oscillation, what you do is you take a rope and tie one end of the rope to the wall, and then hold the other end in your hand, and then keep it tight, okay, so that the rope doesn't have a parabolic structure there, okay. So you hold it tight and then start oscillating. That means your hand, you move up and down, so that the wave is you are able to see the wave actually. So that is how you simply do your experiment in the waves and oscillation, which means that what is actually happening is that there is an initial disturbance. So in an experimental situation, there is an initial disturbance is there. You are going to oscillate, or you are going to move your hand up and down sinusoidally. That is called harmonic way. In an harmonic way, you are going to move your hand up and down. That is called initial disturbance. That initial disturbance is what is going to propagate, and that's what we mean to say. If your initial disturbance is properly maintained, then a sine wave will naturally propagate. If the initial disturbance is some hopeless way you oscillate your hand, then that kind of a structure will propagate. So you now see how the sine wave is coming into picture. So sine wave will propagate only if your initial condition is like that, or initial disturbance is like that. And in the similar situation, in the case of the electromagnetic waves also, the electromagnetic waves are generated by, remember, electromagnetic waves are generated by harmonic oscillation of the electric charges. Harmonic oscillation. You know what is harmonic oscillation? It's simple harmonic oscillation. So the charge has to oscillate simple harmonic way, or we say that the charges should execute a simple harmonic oscillation. If it happens, then the disturbance will be sinusoidal in nature, and therefore that sinusoidal wave will propagate. And we say that the propagation of the wave is represented by a sine wave or a cos wave mathematically. So the reason is clear. If you don't oscillate in an experimental setup like that, then the resulting wave will be very complicated. We do not know what kind of mathematical equation to write for that wave. So in order to avoid all these difficulties, our initial disturbance to our physical system or an experimental setup should be made in such a way that the wave emerging is sinusoidal in nature. And if it is the case, this is important, this f can be replaced by sine. That's what I have written here. All other things are same, only f has to be replaced by sine. So f represents any function, that is what is arbitrary function. Now instead of having that kind of chaotic situation, we will make it very particular that let us generate only the sinusoidal waves, in which case either I can write a sine wave or I can write a cos wave. So therefore, now the ultimate point is, what is the ultimate conclusion is that capital F, let us say that it represents general solution to the wave equation, is given by these two combination, one representing the wave propagating in positive x direction, and this one is representing the wave propagating in the negative x direction. So this is how the story comes, and then now you are able to understand at least the appearance of x minus vt. But still there is a problem. Actually, the problem of the physical dimensions, units and dimension, that is not yet solved. So I'll now explain that what is the difficulty with the units and dimensions. Okay, first thing what you understand is that when you are considering x minus vt, I would like to know what is the overall dimensions for x minus vt. X is in meters, right? So v into t should also be in meter. So after subtracting, I must be having meters. So the square bracket represents the units and dimension. That's what it means. So okay, so meter will be the ultimate dimension that I have. So now why do you want to worry about this? Is that we are going to calculate sine of x minus vt. That means what? Sine of some quantity whose dimension is meter. That is, you say that sine of 20 meter, sine of 25 meter. Is there any meaning? That's what we are asking the question. So here the point to be noted is that the quantities like sine or cos or e to the power function should have no units for its arguments. This is by definition from mathematics. Okay, what do you mean by argument? Argument means the quantity inside bracket of the sine. Sine of something, that is argument. Cos of something, that something is the argument. e to the power theta, the power is the argument. So that power should that particular quantity should not have any dimensions, only then your calculation is correct. But if I am having sine of x minus vt, then I'll be having sine of 25 meter, then there is no meaning. Meter should not be there. That is where the trouble comes. So therefore, our conclusion is that writing down an expression like sine of x minus vt is not acceptable. So there is a trouble with the units and dimension if you are going to write down an equation like this. So the question is what to do. Okay, that's a simple solution. Okay, this is the quantity that is having the dimension. Let us make it non-dimensional. Non-dimensional means what? That meter we have to cancel. Now how do you cancel the meter? You divide by another quantity whose dimension is also meter. That is called a non-dimensionalization. Non-dimensionalization means whatever unit is there, the same unit you divide, so that ultimately you will be having a dimensionless number. Okay, so now you ask the question, by what quantity shall I divide? Okay, you can divide by anything. It's only a number ultimately. Okay, lambda is a number, and you know that in the case of the wave phenomena, lambda is known as the wavelength, and wavelength of the number, wavelength of a particular wave is a number finally. So dividing by a number, nothing will happen to the graph. So the graph will be there as original. Some scaling will be there. That's all about it. Structure will not change. So therefore, at the same time, lambda has the dimensions. Okay, if lambda is say 1 meter, for example, then automatically meter will get cancelled. So now I will be having a dimensionless number. So now you understand that because this is connected with the same wave, that is the reason why we are dividing by lambda. It is not that you close your eye and divide by 1 meter. That is wrong. That you should not do. You have to divide by a quantity that is relevant to the phenomena that you are talking. Right now we are talking about the wave phenomena. So related to the same wave phenomena, what quantity is having the dimension of meter? Like that you are asking the question, and you discover that wavelength is the quantity, and therefore you divide by lambda. So that's all about it. So this quantity is the one that I want, so that it is dimensionless. But however, practically speaking, you know that 2 pi f, when 2 pi f is there, we can know what is known as the angular frequency can be calculated. So the factor 2 pi comes into picture. So it's only a matter of convenience. So multiplying by a number, dividing by a number, there is no trouble. So multiplying by, pi is just 3.14. So multiplying by 2 into 3.14 doesn't destroy the original structure of the graphs that we have seen. So in case if you multiply by 2 pi and redraw the graph, nothing will happen to the structure. Everything will remain same. And therefore, instead of dividing by lambda, it's okay, you divide by lambda, but multiply by 2 pi. 2 pi doesn't have any units. Okay, we don't, as I already told you, radians will not be considering for the units, and therefore no need to worry. So 2 pi will not affect the entire calculation. So the quantity inside the square bracket is completely dimensionless, and therefore now we are mathematically we are ready to calculate sine of this quantity. Okay, that's fine. And 2 pi by lambda, of course, from your elementary waves and oscillation course in BSc, you know that 2 pi by lambda is what is known as the wave number, and we represent it by the quantity k. So if I multiply that, this is k, so k into x, so that is this quantity, and then k into v. This k into v is actually omega, which is also known from waves and oscillation. That means you have a wave number multiplied by the speed of the wave, that will give you the angular frequency, which is equal to 2 pi f. That's the meaning. So you see now how you went in a roundabout way, and then you discovered sine of kx minus omega t. How kx minus omega t comes into picture. So that is the story which is now clear how it has come. Now, okay, let us now make some more interesting points. So the first point is that you need not write only sine function. You can always write cos function also, because every sine and cos function are acceptable solutions, and therefore both sine and cos you'll have to consider. So that is the point. Okay, let us see how to deal with both of them. I'll move down now. Yeah. So the point that I am trying to say is that why only sine? So as you can see that e to the power I theta. So this is actually e to the power I theta. E power I theta, you know how to write? Cos theta plus I sin theta. So therefore, I will be able to simultaneously consider the sine wave as well as the cos wave under consideration, and plus I represent only a linear combination. I is just mathematically it's a number, so it is still a valid combination, like linear combination. There's no trouble in that, and therefore we are essentially considering a linear combination of sine wave and cos wave simultaneously. So that is the reason why we ultimately have e to the power of I into, why I into came, that is because cos theta plus I sin theta, that's all about it. And kx minus omega t is coming here, and simultaneously sine and cos is what has become e to the power I, and that's all about it. So this is all about considering the expression for e to the power of I into kx minus omega t to the solution to the wave equation. So this is first part. So at least one big part of the understanding will be clear, and once this is clear, let us go back to the uh, wave equation and then verify. The point that I am trying to say is, okay, our conclusion is now clear that an equation looking like a e to the power of I into kx minus omega t will be the solution to the wave equation. That is our conclusion. So we have done all these things, but then you cannot close your eye and say that that is always a solution unless you check it, because we have not done a mathematical solution methodology to the differential equation. We have not done that, but instead we have considered some elementary basics from drawing the graphs, and then we have came up like that, and therefore we believe that it is a solution to this differential equation. But however, you will have to be careful whether it really satisfies or not, and that's quite simple. What all you will have to do is that you take this and then substitute into this wave equation. So that's only one line. Let us substitute it. By substituting, what happens is I'll have to differentiate 2 times here. That is why this has come. If I differentiate one time, I'll get ik. This ik will come with respect to x. And if I do second derivative, once again ik will come, and the entire expression will be intact here. So that means I have actually calculated the second derivative here. Similarly, right side I will have to perform the second derivative with respect to t. With respect to t, what will come out now? I into minus omega will come. So I into minus omega will come every time I differentiate with respect to time. I will write down that now. Then into, open a bracket, then I into the minus I omega, once again minus I omega. And that's all. So let us therefore simplify. Once this is over, we are interested to check whether the equality is valid or not. If the left side is equal to the right side, then we say that okay, it is satisfied, and we agree that that is a solution. Whether it is going to happen, that's what we are going to see. Now we'll see by simplifying, we can actually cancel this e to the power on both the side. Okay, so after cancelling, what happens? Let's say I times I square. So I square is a minus actually. Okay, let me finish the remaining quantities. I think that's all about it. So that gives you omega square is equal to k square by v, k square v square. So let me take the square root now. Here there's a minus is missing, right? There is a minus here, minus omega square. So how minus omega square? You see, I missed it. So this minus into minus is plus. Then I into I into I is I square. So I square is minus 1. That minus 1 only just now I have put. And afterwards you have a omega square that is already there. So one minus was missing. So this minus has to be transferred here. Therefore this will become a plus now. Okay, that's all. Now I will take the square root. So square root means always plus or minus. Okay, so this is clear. Now we'll have to be careful about the plus or minus. Okay, let me explain first and then write down. Whenever you take a square root, you'll have to put a plus or minus. So that means either a positive value can be considered or a negative value can be considered mathematically. That's fine. But then you ask the question, what is omega? Omega means what? Frequency. Frequency of the wave. And frequency of the wave, do you think it's a negative value? You already know what is the frequency of the wave, isn't it? So frequency cannot be a negative value, similar to the radius of the circle. You can't draw a circle with negative radius. Similarly, you can't have a wave with negative frequency. Therefore, even though mathematically minus value will come, now we want to clearly tell that if at all any minus value comes, you have to throw the minus and take only the number. Now, how do you say that? How do you say? Means you put a modulus. That is what is called the absolute value. So therefore, now I can say that that is equal to k into we put an absolute value for the k. That's what we mean to say. Now, in fact, you can ask the question, why don't we put an absolute value for v also? But velocity is already a positive quantity. You don't get any, in your calculation, you don't have any negative value. So that is why we don't worry about this. Now in our calculation, the new quantity entering into picture is k. That is a new quantity. So because this is only the new quantity, we are going to put the restriction that the k value should be positive only. If at all minus comes, you simply throw the minus and then take the number only. That is the meaning of this absolute value. And that's all. This is the equation that we are getting. So what is our conclusion? Our conclusion is that the wave equation is not automatically satisfied. You thought that, so what did you initially thought? You thought that e to the power of I into kx minus omega t will be a solution to the wave equation. By that, what it means? It means that the left side should be equal to right side. But here you see, left side and right side, we got two different expressions, which means that what we have to now say is that we have to put an if condition. So if this particular condition is satisfied, only then e to the power of I into kx minus omega t will be the solution to the wave equation. Like that, you are right. So that is what is our conclusion, and therefore I'll write down that. So this particular wave, the wave equation, it is not naturally that both sides are equal, and therefore I'll write down the meaning of this particular conclusion. So if this is the equation number 1, then we say that if the equation number 1 is satisfied, only then we can say that e to the power of kx minus omega t will be the solution to the wave equation. That is our conclusion. Therefore, the equation number 1 happens to be an important equation. You cannot forget it. So because that is very important, practically also it is important, this equation is known as dispersion relation. So dispersion relation means it is the relation between omega and k. And this is generally important. So why it is important? It is important both mathematically. Mathematically also it is important, and experimentally also it is important. Experimentally, this represents a dispersion phenomena. So when a wave is propagating, the wave may disperse as it propagates. May means may not also. So some waves will have the dispersion, some waves will not have dispersion. So therefore, the phenomenon of the dispersion will be there in some wave propagation, especially if the wave is propagating in, say, dielectric, let us say fiber optic material. That is one option, or that the wave can propagate in anisotropic crystals. In such situations, what happens is dispersion is unavoidable, and you will be having the dispersion. But interestingly, what happens is when the wave is propagating in free space, namely the vacuum, dispersion is not there. So we have the absence of the dispersion phenomena, and that is the simplest one that we can have both mathematically as well as experimentally. So the consequences of dispersions are very important, and that's why I am actually writing the very important here. So all these things are clear, and now we are having the exponential as the possible solution to the wave equation. So we would like to understand the e to the power I. You have an e to the power I there. So that we would like to understand a little bit, and that's quite simple. We will see this. So what do you mean by e to the power of I into kx minus omega t? If you explicitly write down, it will be clear. It's actually cos theta plus I sin theta. So theta is actually kx minus omega t. So I am writing cos theta plus I sin theta Euler formula. So that is clear. And if it is the case, you ask the question, what will happen if I attach a minus sign here? So you put a minus sign, that is minus of that. You attach a minus sign and once again expand using the Euler formula. Then I will be getting cos theta minus I sin theta. That's all I get. Okay, mathematically speaking, what happens is, this is a linear combination. You understand what is linear combination? This is one wave, this is another wave. These two are combined. In what way it is combined means it is linearly combined. Linearly combined means I don't have powers, like power means other than 1. You don't have cos square, you don't have sine square, you don't have sine cube, you don't have any other power. You have exactly power 1. So such combination is known as a linear combination. And this being a number, of course, this is mathematically speaking, constant should be there. You can have 10, 5, 3, and in this case square root of minus 1. So anyway, it's a constant. So there is one constant here, 1 into, so constant into cos function, then another constant into sine function. The same thing is true here also. Whether it is plus I or minus I doesn't matter in linear combination. In linear combination says that a constant should be there in the middle, and here a plus I is there, here a minus I is there. So both of them are constants. Instead of one constant, you have another constant. That's all. So ultimately speaking, this is important conclusion. The conclusion is, what is the difference between e to the power I into this much and e to the power of minus I into this much? What is the difference? That is the question. The answer is there is no difference. Literally speaking, each one represent one linear combination. So this is also a linear combination. This is also another linear combination. And in order to get the general solution to the differential equation, you have to consider all the combinations. Then only general solution will come. And therefore, we will have to consider all the linear combination. Therefore, we will have to add both of them, so that I will be considering all linear combinations of the solution. And therefore, we will be adding this plus this would be the general solution. So that is how we write it. So whatever I told, I explained you. And the important point, yeah, here it is, I didn't explain. The important point is that whether you write the first version like this or second version here with a minus sign, first version is plus I, second version is minus I. Whether you write this way or that way, both of them will representing waves traveling in the positive x direction only. That is important. I am putting a minus I means not negative. So that like that, that is why that is the purpose of this lecture actually. Okay, this minus doesn't tell that wave is propagating in the minus direction. So you'll have to always see what is the quantity attached with the velocity, because you should always remember x minus vt, right? So which is the quantity associated with velocity means omega. This is the quantity. So this is actually vt. So when along with the vt there is a minus is there. Therefore this is traveling in the positive x direction. Here also minus is there. Therefore this is also representing a wave in the positive x direction. Therefore all of this linear combination, they all represent traveling waves. This is an important word. When you are talking about waves and oscillation, you have standing wave and a traveling wave. So this concept is important. In the case of the electromagnetism, you can have the most of the time you'll be having only the traveling waves, and standing waves generally we don't do it. Okay, but sometimes you can see whether standing waves are possible or not. Sometimes standing waves are not allowed by Maxwell's equations. Okay, let us not worry about the standing wave now. The point to be noted is that this equation e to the power of I into this represent traveling wave, not the standing wave. That's the point to be noted. And everything is only a linear combination, and therefore we will have to consider this plus this as the general solution to the wave equation. So that is the first point. And the similar thing, I would like to write a very similar thing once again, so that will be clear now. Let me write down what will happen if it is going to move in the negative direction. So just now I said that everything is moving in the positive x direction. So question naturally comes, suppose if it is moving in the negative x direction, okay, suppose if it is moving in the negative x direction, how the equation will look like? That is the question. Answer is very simple, that you replace the velocity by negative velocity. That's all about it. And in equivalently what you do is you can represent or you can replace k by minus k, because this is an equivalent representation. If you are going to work with the x minus vt version, it's fine, we can replace v by minus v. But since everything is been already translated in terms of wave vector, the wave vector is going to tell you the direction of propagation. Because of that reason, every k will be replaced by minus k in that equation. If you replace, then it will represent opposite direction. I didn't say plus direction or minus direction. If k is your original direction, then after replacing minus k, then that will represent wave propagating in the opposite direction. Okay, so now in this one, in which direction it is traveling means positive x direction it is traveling. Therefore, after making the substitution, what happens is the wave will be propagating in the negative x direction. So that point is clear, right? Okay, so therefore you take this particular expression and then substitute or replace k by minus k. Okay, let me therefore write down like that. So e to the power of I into minus kx minus omega t. So you see that this particular expression only I am considering. This k is replaced by minus k. All other things are retained as original. You should not change any other thing. That's important. And once you finish this, after that you can do simplification. That is okay. So let me do therefore the simplification. I'll take a minus common now. That's how it looks. And that is first part. And second is this one. So there is a minus I version is there, right? This one. So that also will let us write down. Minus I, replace now, minus k. The rest of the thing is same. Now you simplify. And that's all. So these are the two expressions that we got. So now you got the conclusion. Okay, I'll write the conclusion. Okay, first I'll explain. So now what happened is, these are the two equations, or we say that if at all the wave is going to travel in the negative x direction, the equation should appear either this or a linear combination of these two. That is acceptable. So, and anything that is there in the previous one is going to represent in positive x direction. Now you understand which equation will be propagating in which direction. So okay, so that point is clear. So I will write down this. So that is the almost important things are over. So I think this conclusion, whatever I explained, there are 4 points are there. 2 of them I have written. I would like to write 2 more things. I'll write here itself. Here space is there. Yeah, that's all. So now what happens is, this is the overall conclusion. You have 2 ways of combining things. So you see that there is a I version, minus I version, and there is I version, there is a minus I version. So this I version minus I version is linear combination. Is the point clear? And then you'll be having either a k. I mean, after of course, after k is simplified, you got the sign changed here, and therefore we can see along with the velocity component. If you have a minus vt, positive x direction. If you have a plus vt, you have the negative x direction. So negative and positive direction should be confirmed from the velocity, that is vt component. That velocity only got converted to omega, right? So that's a point that you'll have to remember. So from the vt component, you have to decide whether it is positive x direction or negative x direction. And from the I, that means whether it is I or minus I, that is only linear combination. So don't think that I means positive direction, minus I means negative direction. That this confusion will come. That is why all this explanation comes into picture. Now this is clear. Now the equivalent, what I am trying to say is, one book will write, if you are going to read multiple books, okay, suppose if you are going to read different books, what happens is, some people will write kx minus omega t, some people will write omega t minus kx. You see that there is a flipping is there. So whether the flipping is allowed or not, the doubt will come. Suppose if I flip omega t and kx, whether the wave will propagate in the opposite direction, that kind of doubt will come. So now these doubts will be cleared. How it will be cleared is, you yourself can flip and write, then what will happen, you can verify and then check what is happening to the vt component. Now that is what is very important. You'll have to check, you should remember, you'll have to check always the vt component and then decide what is happening. And from the appearance of these two, as you can clearly see that this expression and this expression are looking same. Okay, even after flipping, it looking same. That means basically for clarity, you can use the cos theta plus I sin theta, but this being a simple situation, you'll be able to feel that even after flipping the omega t and kx like this, still it is traveling in the positive x direction. And similarly, in this particular case also, this is traveling in the negative x direction, as it is written in yellow color. Oh, there is I forgot to put a plus here. So you put a plus here, so that both of them are plus. Here it is there, right? Actually it is instead of writing kx plus omega t, I am writing omega t plus kx. So this term is coming here and that term is going there. That is how it is written in other books. For positive there is no trouble, but when minus comes, doubts will come. Now all the doubts are clear, and now you'll be you can confidently say what is the appearance of the solution, I mean the appearance of the equation corresponding to which direction it is propagating. So these are the actually the today's subjective. So with this I would like to stop. Probably I am interested to discuss about this. Okay, let me therefore see here. So I think today's objective, primary objective, is the learning the appearance of the solution, and then attaching the direction of propagation. That should be clear, and also the linear combination. So that part is, I think this is fairly covered, so that doubts are not there. The point is that in the next class, okay, I would like to explain how these equations are directly connected to the electrodynamic wave equation. So that is the actual plan for the tomorrow's or the next class. So next time when we meet, we will see how to write down the solutions based on today's discussion. Okay, so I'll stop here.